Okay, so welcome everyone. I'm Vinayak Bhatt. I'm a graduate student in University of Kentucky, and this workshop will be on intermediate Python for chemistry. Uh, I run workshops every month, and if you need to find some details about the workshops, please follow the Chemistry with Code page on Facebook, so that you keep in touch with the activities that I'm conducting every month. And the workshops will be for free, and it's usually at this time of the day that I conduct it on Saturdays. So the next workshop will be on automation in chemistry. We'll be using Python again, and that'll be on June 26th. That's almost a month from now. And again, the same time, 10 p.m. or 10 a.m. to 12 p.m. EDT. That we'll look into how to use MongoDB database. That's something where we can store data for automation, and we'll look at Fireworks, which is a Python package to run automation in chemistry. So the tickets will be available soon. So do follow the page for more information. So today's workshop, as the details, as the page on Facebook or Eventbrite showed, there'll be RDKit and PyMedGen, and we'll try to put in some of machine learning into both of these. Because of time, that is 2 hours that is allocated for this workshop, I may not go over the other package that was mentioned, which was AAC. So we'll have RDKit and PyMedGen along with some basic introduction to ML, and you'll be training models to predict some things. So if you have any question, so the question is this a beginner version of the workshop? Yes, this is a beginner version of the workshop, but it'll be good if you know some Python, because everything that we do will use Python. And I'm not going to greater details into how to define a variable and do things, but you can follow along. This is a hands-on workshop, so you can just follow along. The code is there. You have some description of what is going on, so you can try doing it. But yeah, some Python knowledge will of course be helpful. So yeah, so we'll have an hour for RDKit, and there was a pre-workshop survey in which I found that a lot of people were interested in RDKit and some machine learning with RDKit. While there were only few folks with PyMedGen interest, but I'll just spend almost equal time, if possible, on both of those. I may increase the time that we spent on RDKit though. So we'll be using Google Collab for doing this, and I'll be sharing you the links for the collabs. And once you get the links, I'll show you how to work with that. And if you have any questions, you can just turn off your mic and ask me questions, or you can just type it in the chat and I can follow up. Okay. So do you have any questions at this point?
Yeah, one question. Are you going to make a workshop about ACA and another time?
Not completely AC. I think it'll be more on automation. I can put that stuff in the automation too, because in AAC, what we can do is run some codes directly in AAC. So I'll try to do automation in there. So I try to put that in the next workshop, which is on automation, because there are some codes for running molecular dynamics or running some DFT calculation that you can do with the AAC. So yeah, I'll definitely cover that in the next workshop.
Okay, thank you.
So, okay, so let's get started. I'll share this links with you, and I'll tell you how to use those, and let's go forward. Okay, so this is the first link for the RDKit. And let me share screen. So can you guys see my screen with RDKit open? The notebook. Yes, cool. So this is how we are going to use Collab if you have not used it before. So first go to File and try to save this book in your save a copy in your drive so that you can get your work that you have done saved. So if you try to work in this book and try to open it later, if you have done any additional work in this book, it will just disappear. So this is how we are going to start. So go to File, Save Copy in a drive. So once you do that, you'll see a copy being created, and that is what we'll be using for that. So you should see copy of introduction, RDKit and ML. So let's start with this. So is everyone able to do that? If yes, you can put a thumbs up or something else. You can put in reactions. Let me know if it is working for you guys. Okay. So a couple of yeses, and okay. So RDKit, if you look at the installation of RDKit, and I'll also tell you how to install RDKit so that you know how things work in packages and other things. So if you go to installation of RDKit, so this is usually installed with conda. So conda is a package managing software that you can use, and you see that it needs conda install. So we this by default there's no conda installed in Google Colab, so we would need to install conda, and this is how we would install it. And to run a cell, what you can do is either you can play on the play button here, click on the play button, or shift enter. So pressing that will start running the notebook. So there are multiple options here which you can explore later on, but we won't use any of these things right now. So we'll be installing conda, and this is how we are going to install conda in this. So click on this play button, or just press shift enter, and it should start running. It'll take a minute or so to run it. So if you're at this point where it is running, you're good to go. So you see this, okay, so you will see your session crashed for unknown reasons. And this should appear because we are installing something. So if you see this, your thing is done, right? Okay. So did people get this? Your session crashed for unknown reasons. Are we at this point now? Yes. Okay, I got it. So let's go to the next one. So to check whether everything is okay, go to the next cell, click on it. You'll see it's installed. Right. So now you can install all packages that can be installed with conda. And this, if you go here, it says where is it? Okay. So conda install. So you can install RDKit. So this how we install it. So RDKit install and click it, and it should install RDKit for you. And we don't have these packages in Collab. That is why we are installing it here. But there are some other packages for machine learning and other things which are already in there. So we'll not try to install those. So this will take some time to install, and then we'll get started with the molecules and doing things in RDKit. So everyone done with installation? Done. Okay. So you can start with the next one, which is importing. And for those who have not used much of Python, what we do is we try to get those definitions from a particular library. So we'll say from RDKit import chem. So chem has some definitions of some functions that we are going to use, and these are the core definitions in RDKit. So this is how you'll be creating molecules, reading molecules, and doing stuff. We may not use this function, but I'll show you how to use it sometime if possible. And this is for displaying the molecules. So there's descriptors that we are going to calculate, and we'll be using pandas. So pandas is a Python library for storing data in a table. So this is a very nice library to use for machine learning stuff. And we'll use NumPy, and NumPy is for math stuff, and we'll use plotting libraries. So first start with, let's go to this page, which is RDKit. So you have a nice molecule here, right? So this molecule, if you want to represent it in some way, you can give XYZ coordinates and atoms and other things like you do in a normal file. But if you want to use it in a machine and say that this is this molecule that you're seeing here, how do we do that? So there is a way which is called smiles, in which you represent a molecule with a string. Some of you may have be familiar with this, but this information is for people who are not aware of smiles. So in smiles is a way of representing molecules. So if you want to say CCC, so this is a propane molecule. So this is how you would say, okay, I want a propane molecule. And you can just add CCCs or double bonds if you want somewhere, or even triple bonds. Okay. So this is how we are going to represent molecules, and CCC, and if you want O, OH. So this is a string smiles representation. So it'll be a string, and that is how we are going to do stuff with this. Okay. So I hope you guys can still see my browser when I'm moving from one tab to the other. Yes. Okay. So that is what we are going to use it. So we can create molecule objects, just as we saw over here. This is a molecule, so we'll try to create it in Python and RDKit to be specific. So you'll say chem is the core definitions. So it has a function called mole from smiles, and we'll just put in smiles. And if you just run this cell, you'll see that we have created a molecule. Okay, so 4 carbons and a single and a double bond. So once you create a molecule has atoms in it, right? So there are atoms and bonds. That is how a molecule will be defined in RDKit. And to get atoms, what we would need to do is mol.get atoms. Okay. Error on your page. So if there's an error, that will probably be if you have not installed the RDKit. So I would just say you just go over the first cell and run it again. First cell, second cell, and third cell. Okay. So the package installation would be a problem if you run this cell, the importing thing. If you see an error here, that is because of RDKit not being installed. So just try to start from the beginning, and it should work. Okay. So I'll proceed in interest of time. So you'll see this, and if you want to get atoms from it, so you want to know what atom is connected in here. So what you can do is get atoms. So, and then if I print this out, you can see the first atom has atomic number 6. Second atom has atomic number 6. So when you generate the atoms object from molecule.getAtom gives you a list of atoms, and each of those atoms have different things. So I'll say get atomic number. So atomic number for all of those atoms are 6. So that is how you do it. And if you need to know what methods are really present for atoms, so you can say dir atoms, and you can see what all is present in there. So you can get atomic number, you can get bonds, and you can get number of explicit hydrogens and total valence and whatnot. Okay, so this is what you do. And regarding creating of molecules, right? So it's not only from smiles. There are multiple ways in which you can create molecules. And let me add the code. Yeah. Okay. So if you say chem dot. So if you see mole from, so these are the things that you can do, not only smiles. So you can use a FASTA, you can use a ng, you can use a mole block, you can even use a PDB file to load it. You can do it from smarts, sequence, all of these. So I just showed you one example wherein we use smiles because it's easier for us to just type in something. So I just use smiles, but you can use any of those to load in your molecules and get the molecules from there. Okay. So once you have molecules, you can get atoms from them, and atoms have these many properties that you can explore, and the same goes with bonds. So you can say molecule.getBond, and this will get you bond. And over here, I'm looking at the type of bond. And if you look at the molecule that we had was single, double, single bond. And that is what it shows. Yeah. So single, double, single. So all of these are basic commands. I'm not going to go into too much complexity here. This is just to give you an idea of what you can do and the things that are available, and you can explore from there now. So, and if you want to see what things are present, again, dir would of a bond would give you all the methods that are available for this. Whether you can see whether it's aromatic or not, whether it has an atom, get the atoms connected, and all of those. So do you have any questions at this point of time? So if not, we have an exercise here. You can try it yourself. So in this, we are trying to find the molecule that has the highest number of atoms and find a molecule which has the highest number of rings, and find the highest number of double bonds, molecule with highest number of double bonds, and largest number of non-carbon atoms. So to do this, I already have written a small code for you wherein you will get the smiles, and these are from the GDB database, and you can just run it, and over here we have around 133,000 smiles. And if you run this code, you'll be getting those smiles here, and you can start writing a code. At least try to get the molecule with highest number of atoms. And how do we get that is you have mol.get atoms. You can also see how many number of atoms are there. So mol, if you look for dir of mol, you'll get many options in there, and get number of atoms is one of them. So you can run a for loop and see the molecule which has the highest number of atoms. At least go to the first part, it'll be a good exercise. And if you want, you can use a smaller version of this. Say smiles is created for you. So you can say smiles list 500 and slice the list and take just 500 of them and do this part. If you have any questions, let me know. We'll spend like 5 minutes on this so that you guys are familiar with creating molecules and then trying to do some manipulation, accessing the atoms and bonds. And if you have any questions, do let me know. So for people who have no idea of what to do, so I'll just write a pseudocode here. So your thing would be just to loop over all smiles. First thing, you'll write a for loop and then check for, this is for the first one, which is highest number. So loop for smiles, and then in each loop you'll say generate the molecule object, and then count number of atoms. Put a condition. Condition to find whether it's the largest one. And just enter. So anyone done with this code to get the molecule with highest number of atoms? Do you guys want me to work through this code for you? So what do I do first is just write a for loop, right? For smile in smiles list. I'll just say let me use this 500 because 100,000 is a big number. And generate molecule. Let me say M is M dot mol from smiles, and then smiles. The highest number of atoms is 9. I think highest number of atoms would be 9. But I think you're looking at the you're looking at this one, which is get atomic number, and that is 9, I think. And because we have carbon, hydrogen, it just is carbon, nitrogen, oxygen, and fluorine. So you'll get atomic number 9. So my intent here was to have the number of atoms. So you can use get num atoms, and that is what we'll try to use. So let me quickly show you. So I say mol dot num atoms. So this is what we'll be using to do it. So this is 4 atoms over here, and these are all heavy atoms that we are counting. So we had 4 carbons, so 4 atoms. So we'll be using that to get it. Okay, I think you use a small set. Yeah, that's fine. So as long as this is working for you guys, so you can just say we usually do this. So max atoms is 0, and then count atoms if mo m dot get is greater max. And you have your condition there, and then minus is if this is 2, max miles is equal to m dot m. You can just save this miles if you want. So and if you run the code, so max miles now has that. So I'll do chem dot mol firms miles, then max miles. So yeah, 1, 2, 3, 4, 5, 6. Yeah. I use a smaller set. So depending on this, you can do that, and then say you get if you want 6 for this. Okay, I use a smaller set here, so you can use a larger set and see what you get. Yeah. So this is just an example, just for practice, when you can generate smiles and look at the functions that are available and do stuff. And you can even find the number of rings in that. So there are multiple options, just like get number of atoms. There are other options too, like get rings and number of double bonds and other things. Okay, so is everyone comfortable until this point? So if you have any questions, please let me know. Okay, so this code will be available for you because it's saved in your drive. You can go over it again and again and try to solve this. But in interest of time, let's just, is it possible to count hydrogens also? Okay, I'll be, yeah. So there is get explicit hydrogens or something. So I think you can do that. So let me see. So mol dot get the number of heavy atoms. So yeah, we'll go into that question, which is it possible to count hydrogens also? So we have not yet added hydrogens to this. As we see, the number of atoms that were shown here was 4, and when we count number of atoms, it just gives 4 because there are no hydrogens added. So we'll go into the part right now. What what needs to be done there. So so this thing that you generated has is a 2D structure. It's not a 3D structure. So if you want to calculate some descriptors like calculate a molecular weight, you can do that. So if you want to calculate molecular weight of this butene molecule, you get that as this. And those are some 2D like descriptors. But if you want a 3D descriptor, which is a radius of gyration, that would not be possible right from SMILES. But if you use some other things from XYZ or 3D coordinates, you could be able to do that. But in this, it is not possible, right? So because you only have 2D things in this. So the problem comes because there is a, it says over here, molecule has no conformers, right? So there are no XYZ coordinates defined for this. So that is where we have a problem. And if you see this get conformers, it says 0, right? So it needs some confirmation for it to calculate the radius of gyration, but molecular mass it can calculate from the formula that is there. So to generate the conformer, we first need to add hydrogens. As we saw, we did not have hydrogens. Let's add hydrogens with this command, which is add hydrogens, and pass in a molecule. It will give back another molecule. And what I'm doing here is you can save it to save a molecule back as a mole block too. So mole block is what you will see right now. So you generated a molecule with hydrogens now, because we said add hydrogens, and RDKit will add hydrogens to it, and it'll generate a molecule. Right now, no, it'll generate a conformer because we added hydrogens now. So you see this is a 2D again, because these are the XYZ coordinates here, and you see all Z's are zeros. So that means it's a 2D conformer that you have, and RDKit shows that RDKit 2D. So this is a mole block, and you can read in something like this and get XYZ coordinates directly into the molecule object, or we can create it. Okay. So over here we created, we added hydrogens and looked at this conformer now. So there are no conformers yet because we don't have 3D coordinates. Okay. So to generate 3D coordinates, what we would do is use this function, which is called Embed Molecules. Okay. So when you say Embed Molecules, it's going to generate a 3D conformer for you, and you can see it's a 3D conformer. Now the number of conformers is 1. So this generation, there's an algorithm which does it, and you may not always get the least energy structure. So there are ways in which you can find the minimum energy structure and other things. And this is a very good topic of research that people try to do, is to find the most stable conformer. And people have been writing code for that, but this is just one conformer that we get out of RDKit. Okay. So we say embed molecules and pass in the molecule, and make sure you always add hydrogens so that the generation of the molecule is better. And now we see it's a 3D, and we have X, Y, Z coordinates, all of them. So the Z coordinate is no longer 0. So do you have any questions at this point about conformers? And why do we need conformers? Okay. Looks like no questions. So let's proceed. So you can, in this case, we added one conformer, right? So the number of conformer is 1. You can generate hundreds of conformers if you want, because if you want to sample the space, and how do we choose the most stable one? Yeah, that's a good question. So how do we choose the most stable one? So in this case, it just gives you one conformer. It may or may not be stable when you say embed molecule. In the other case, what you can say is embed multiple conformers. So pass in the molecule, molecule object, which is mole H that we generated with hydrogens, and say we want to generate 50 of those conformers. And if you do that, you'll see there are 50 conformers in this. So RDKit does provide some of this, some energy calculations too. And if you want to do that, there is, let me see. So what is it? MMFF. So you could use any of these force fields. So get molecule force field and then pass in those conformer objects. So get molecule force field. I think like this, if I remember it. Okay, so if you don't know what is happening, right? So I didn't know the exact format of this. So even if you type the wrong thing, it shows you what is needed. Okay, sometimes you may not know what arguments are needed for this. So it says this code is written in C, and there are some functions that convert Python to C, and that's why you see a C++ thing. Okay, so it says this requires a molecule, right? RDKit molecule, force field properties, conf ID, and double threshold. So needs force field. Okay, so it needs force fields, and this is the molecule that we have, and double bond properties. I think there's force field properties again somewhere. So if you let me quickly check that. So yeah, I'll just get back to this. So if you do this, you'll get energies for all those conformers that you have generated, and you'll try to optimize it. So optimize molecule conformers. Yeah. So if I do this molecule conformers, I have generated 50 conformers here. So I should be having energy for all those 50 conformers, right? And this is MMFF optimization. So by default, I think there's something which is done. Let me see. So number of thread max iterations. Yeah. So yeah. So it optimizes it and gives you some energies. So if you just look that up, so you'll be getting energies, right? So you can use this to then see which one of them is the lowest one and select the lowest energy conformer for analyzing. Okay. So this is something you can try. So now let's try to compute volume and plot the distribution from the smiles list. So remember, when you generate it from smiles, you won't have the 3D conformer. So you need to embed a single molecule like this, embed molecule and pass in the molecule to generate the 3D thing. But before doing this, you need to add hydrogens and then do it. So try plotting, at least for some 500 of the smiles, try plotting a curve for molecular volume distribution. And the code again should look like that. So loop over smiles and then generate molecule for smiles, generate molecule, and then add hydrogens. Generate conformer. Once the conformer is generated, compute volume and append something and save that value. So once you add and save the value and out of the loop, once you're out of the loop. So do you have any questions until this point? I'll give you a couple of minutes to work on this code, which is to plot the molecule volume distribution. So if you have any question, please let me know. You can type it in chat. Could we please pass the Collab page that has answers to us? I would have to create it per se, because this code is just for practice, and I haven't had any answers to this. I haven't tried it myself either. So yeah, I'll try to generate one and probably send it to you if possible. So for people who want to put some code for smiles and smiles list, then just say 500 of those and generate molecule. So mole is chem dot mole smiles. And then mole with hydrogen is add H, and you need to pass in the mole. So I did that part above, and then embed molecule H. So computing volume will be compute mole volume of mole H. You want to create a list here. Vols is volumes is this, and just try appending it. Volume start append this, and then you can just plot it. Anything. I personally like to use Seaborn for plotting because it's easier. It looks like somehow it did not generate. I'll just put it right just to get rid of it. Somehow, sometimes the molecule generation is not that good. So the embedded molecule doesn't work that well if your conformer is too tricky. So okay, this thing should work, and it's going about here, and you can see that thing moving. So it does take some time to do that, but yeah, I'll just pause this one. So yeah, okay. So so that code is taking some time to work, but let's move on. So okay, so we'll create any questions until this point, or shall we proceed? So yeah, so that is because I think I have not imported Seaborn here. Thought I had imported it. So if you get that ever SNS, yeah, so you can import Seaborn as SNS, and then so yeah, so you can just add this line if you want. Thought I had imported it. So all these packages are already installed. That's one nice thing about using this. So you can say import this and then plot this. So let me see if that works. If right. So and this is the molecular volume, and just say dist plot. It gives a nice distribution of molecular volumes. So yeah, generating this is a bit trickier when you do have embed molecules and embed molecules. Sometimes the molecule is not too good to do that. But yeah, so you should see a distribution like this, which is nice and good. So moving forward, let's try to be on time, I think. So first we'll create a pandas data frame, because as we see, handling each of the entries is difficult. So if we pass in the smiles list here and say columns equal to smiles, and I just use 500 randomly selected molecules here and create a data frame. What data frame does is it creates a nice table. Yeah, creates a nice table like this, and you see smiles and other things. So you can just keep on adding properties into this now. So you can add something over here. That's what we are going to do, and I'll show you how to do that. And yeah, pandas is this thing which creates nice tables. You can store nice data into this, just like an Excel sheet, and you can play around with this. So a head gives you the first 5 entries of the data frame that we are looking at, but we still have 500 of those entries. So if you want to see all of those, yeah, and it'll show not all of those, but you'll see there are 500 rows in this. Okay. So with that, what we'll now do is we have the smiles. We'll create molecule, which is what is the first column in the data frame? Yeah, that's a good question. So the first column in the data frame is the index, and if you would just create the entire data frame without the sample, it would start with index 0. So it'll be 0, 1, 2, 3, 4, 5, and so on. Let me just quickly show you that. So 4. So if I do this and remove all of them and then say df, so it should start with 0, and it should end with the last number of molecule, that is 13884. But over here we say sample 500 molecules. So randomly choose 500 molecules. So when it randomly chose that molecule, the index still remains. So it randomly chose some molecules, and these are the index of that. Okay. So that is the index of it. Can you please share this link so that I can practice? I'm sorry I joined late. Okay, sure. Let me see where I have the link. So this this is the link, and do make sure you go to File, save a copy in Drive, so that you can work on it later on too, and all your work will be saved. Okay. So here we created this smiles, right? So we can create molecules directly. To do that, we have pandas tools, and this is RDKit thing that is present. So RDKit has a nice thing called tools, and you can see some example here how they do it. You just click on this. So this is something cool about Collab. So if you just hover or something, you can see what is in there. Okay, some examples and how to use it. So over here, we'll add a molecule to the data frame. Right now, we only have smiles, so we'll add molecules to it. And if we do this, it'll add a molecule, and you can see the molecules here. Nice molecules here. Right? So you may get different molecules because it's randomly sampling it. So all of it is not the same. But the intent is this. So we have smiles now, we generated the molecule, we'll generate some descriptors and then try to do machine learning on those descriptors. That is why we are doing this. And DataFrame provides a nice way of storing that data that we need. Okay. So we have smiles, we generated molecule. So let's generate some target values and some descriptors first. Okay. Any questions to this point?
Hello, Vinayak.
Yeah.
Vinayak, can we import directly data from PubChem or Zinc databases?
I think there are ways to do it. I'm not pretty sure about it right now. I don't I'm not sure about that, but I think you could do it somehow.
Data parsing methods we can do it, or
yeah, there are some like FASTA sequence and other things that was there, right? So directly extracting from PubChem, I think it would be possible somehow, but I'm not sure right away on top of my mind.
Okay, thank you, Vinayak. Thank you.
Right away. But yeah, if you get the smiles, you can of course do it this way. One can directly download molecule as STF for smiles, and yeah. So if you download them, you'll be able to do the same thing again. Okay. So here we generated smiles and molecules now. So for molecule objects, we'll try to do some things, and we'll only use the 2D stuff right now and not 3D. So this is how we are going to generate, we generated molecules, right? So let's use the target as the number of rings in the system for this machine learning model. So what we'll do is generate a machine learning model that predicts how many rings are there in the system. That's the easiest thing that we can think of, right? So look at this molecule and how many rings are there. There's one ring, there's two rings, and so on. So this is a simple machine learning model that we are going to build right now. So first, let's create a column and let's add a column called target. So data frame target will be data frame of our mole, and our mole is this column. Right? So our mole is this column that we generated by adding this. So we'll say for each our mole entry that we have, we'll apply calculate number of rings. So calculate number of rings is something like calculate molecular mass or compute volume that we used. So we just pass in a function and say that we want to apply this function on all instances of our mole. So for all of these, we'll be applying this. So if you do that, you'll see a column added to it, which is called target because we called it target. And that is what we are trying to predict now. And our mole apply ring. So this one has one ring, this has one, this has two rings, and this has one, and this is one, so on. Okay. So any questions until this point? Because these are simple things that we would need to generate, and these are the descriptors that we could think of for the target values. So for a machine learning model, what we need is an input feature, a way of saying that this molecule is, if you look at this molecule, this is something with one wing. Okay, so the y value will be 1. The target it's trying to estimate will be 1. The input will be this molecule. But so stored or library of molecules from where we can directly use. Yes, there is some stored library in this, and it's called RDKit. I forgot that name. So there's data for solubility and other things, and you can directly import them. So it's called there's something with paths. I forget that name, but maybe at the end of this I'll tell you what to use that, how to use it. But it's a way you can get a library. So the question was, is there any stored or library of molecules from where we can directly use? So there are some examples in RDKit itself where you have the data for that, and you can directly do machine learning. There are some other databases too from which you can extract, like PubChem, the things where you have properties extracted and do machine learning. So once we have generated the target values, we need to have a representation for the input, right? So we need to somehow say that this is the input representation. For this representation, the output is 1. So if you use the smiles, this is a string, right? So a string is not, there are models which use string and try to do this. So those will be natural language processing models, or NLP models, which try to use strings or words to do the prediction. But over here we'll try to use numbers, zeros, ones, or something like that, and try to represent this molecule in terms of zeros and ones. Okay. And for that representation, which is zeros and ones, we would need to create something called Morgan fingerprints. And generate, I think I should, okay. So I thought I put it in, but you can just Google search for Morgan fingerprints and see what those are. Those are like, it shows what type of atom is there in the surrounding, and based on there's some radius that is needed. And I think I should have put in the link here, but yeah. So you'll get a vector of zeros and ones, and that will be the input for this. So this is how we would generate it. So we would say get Morgan fingerprint vector of a molecule, and do go up to 100 bits, and 100 bits is the number of size that we want, the size of that vector. So it'll be 100 dimension, 100 vector, a row vector of 100 bits, zeros, 1, 0, 1. So all of them will be 100. So you can increase it if you want, and once you increase it, you have a more well-defined representation. So for this case, we'll just use 100 bits, and there's something called radius, and the radius, how large you want the radius to be. So over here we'll use 2, and because this is a vector, we need to convert into an array. So we use this convert to NumPy array function, and that will give us an array back. And this is the array that we will use as the input. So we'll say, okay, we'll generate the input column in the DataFrame DF. So how do we generate that? Is we pass in the molecule object and apply this function for each molecule, which is get input. And if you run this function, now we have created that vector of zeros and ones everywhere, right? So this is the input 0, 0, 0, 0, 1. So this thing is based on how the molecules are arranged or attached in the system. And this will be a 100 dimension vector. So all of these would be, so this is 1, 2, 3 zeros. So it'll be 100 because we have applied 100 bits into it. Okay. So now we have target, we have input, that is what we need. So the input is how this, so we can represent this molecule as this vector that we have, this molecule as this vector, and so on. So this will be the input that we'll be using for training the machine learning model to classify how many number of rings we have in this system. So any questions until this point about generating of Morgan fingerprints? There are multiple fingerprints that you can use, and Morgan fingerprint is one of them. And I think it was Axon chemical fingerprints. So if you look at this, so there are many fingerprints that you can use, and we have used this fingerprint right now. And I think they should have an image somewhere. Yeah, there we go. So it'll be adding zeros and ones, and this is the radius. So we have set it at 2. So it'll be like 2 atoms away. Yeah. So 0, 1, 2 atoms away, and it'll generate a vector like this for you. So it'll be a huge vector of ones and zeros that we have, and we have limited this length to 100 right now. We can extend it and keep on extending it if you want. Okay. So this is how the generation takes place. Okay. So any questions into this? Because now we'll move into training the machine learning model to predict things. Okay. It's like no questions. Okay. So we have the data now, X and Y. So X will be the input, and Y, what is that we want to predict? Okay. What we want to predict is the number of rings in the system. So this has 1 ring, this has 2 rings, this has 2, this has 1, this has 2. So we are trying to predict how many rings in the system given this representation. So the input for the model is the representation that we have created here, the fingerprint, and the output that we expect is tell us how many number of rings you have in the system. Okay, so that is what we are trying to predict. And this is a classification problem. So we'll say we'll have those many classes and say that to try to classify into one of those. Okay. Okay, so moving forward. So we have that data. So we'll put everything into X value and a Y value so that we can split the data. And why we need to split it is we want some part of it to test how good the model is, and some part of the data to be trained, to be used for training. So we'll perform a test and train split for that. So first is input. So input.values gives us all the values in the input column, and then we'll add them to list, and we'll do the same thing for Y. Y is the target, and target.values to list. So I'll show you each entry here. So this is what it looks like. So one of the entries, the first entry, X of 0, looks like this. And if you count the number of ones and zeros here, they should be 100, because we created a 100-dimension vector for us for the representation. And the target is 1. And this target is the number of things that we have. Okay. So we have the X, we have the Y, and now we go into using the model. Okay. So we'll be using random forest classifier. So you can read more about it over here. I put in a Wikipedia link for that, so you can just see how what it does and how it does it. So before training a model, what we would need to do is we need to split the data now for training and testing. So we say 20% for test data. So you can change it, but people usually have 80-20 split, 80 for training and 20 for testing. And we put in the X and Y values, and that's what we're going to get. So we're going to get X train for training and X test for the X coordinate for the X values for testing, Y values for testing, Y values for training. So this is how you create using scikit-learn. All these are statistical machine learning models and not something called deep learning. And I think we'll be going into more deep learning stuff or other models, maybe a couple of workshops from now. So do stay tuned in for more updates on that. So we are using a statistical one here, which is random forest. We say random forest, random state is equal to 42. This is just to be consistent with things. And this is how we are going to train the model. It's model.fit. Yes, what are we going to predict again? The prediction again is trying to predict the number of wings in the system. So this molecule has one wing, this molecule has one wing, this molecule has one, this molecule has two. So again, the prediction is how many wings you have in the system given this representation that we have created right now. So it'll be looking like something like this. So these are your X values, and this is your target value. So target in this is one wing. So the first that we saw had one wing in this. So that is what we are trying to do. So trying to find how many wings are there if we are given this representation. So there are two models we have so far. So the question is, so there are two models we have so far. So we have only one model that we are trying to train here. So that is random forest classifier. And for that, we need some input representation for this molecule, which is the input, this vector that we have. So like this. So this will be the input and this will be the output. So we just have only one model here, which we are trying to train, and which is the random forest classifier. So we are doing classification. So there's only one model. So we say a model is equal to this. So this is the initialization step. We can pass in more arguments in here. If you look at the documentation for this, the classifier. So Morgan fingerprint model is for the same purpose. So the Morgan fingerprint that we created is not a machine learning model. It's a way of representing this molecule. So we need a way of representing this molecule. Smiles is one way of representing the molecule, but it is a string. And we don't want strings. We want to do some fitting, right? So we want to try to fit something or do something like that. So in that case, we need numbers. So we don't have a model here. The fingerprint is a way of representing this molecule. And if you go into this extended thing, they'll show you how to represent that molecule. And each one of them should have a unique fingerprint. That's what the thing is about, generating unique fingerprints so that each molecule can be represented uniquely. Because the model does not know this image, right? It cannot see that image. You can do machine learning models for vision and image analysis, but that's a whole different story. But here we are just trying to have a vector of zeros and ones as the representation for this. And those will be unique. Okay. So coming back to this, initialize the model and then pass in the X train and Y train to train the model. Once the model is trained, we'll say model.predict and X test. So these Y predict are the values that the model predicted given the X test values, and X test values look like this. So it is trying to predict this one now. So Y predict will be those values that it predicts. So when we run this, I think it's pretty quick because we have a small data set. Okay. So once this is done, we need to somehow see how good that thing is. So we can go with a confusion matrix to visualize how good this model was. And if you try to plot it, it'll plot you some values. And in this case, the x-axis is the true value. So that is the actual Y test, and that we calculated here. So these are the exact or true Y values that we have along the x-axis. And the Y values that it predicted are along the y-axis. Okay, the target values. So how do we read this? Is something that is truly 0 wings is actually classified as 0 wings. So it's 100% accurate for molecules with 0 wings. If you go to the number of wings that are 1, so there are 28 plus 5 molecules which have 1 wings, but it predicted 28 of them to be 1 wing and 5 of them to be 2 wings. So you see there's some discrepancy here, but this is a simple machine learning model, right? So you can try to improve it later on and see how it is. But yeah, so if there are 2 wings, it try to predict 17 of them as 1, 16 of them as 2. So you see that as we go down, it does not predict it too well. So something that has 6 wings is predicted to be 1 wing. That's how you're going to read this. So if everyone is here, it means that you have successfully trained a machine learning model to predict the number of wings in the system. This is a very simple model which you can intuitively, which you can visualize it to, like say, okay, this is 1 wing, right? So you can see those wings and say how good the thing is in classifying it into all of these. So any questions at this point? So yeah, SNS.heatmap is to generate some heat map like this. And we are going to plot this confusion matrix, which consists of Y predicted along the Y-axis and the Y test. The test is the 2 values for the number of wings. So if you have done this, what you can now try to do is use the same thing and see whether using a higher value of number of bits improves this model in any sense. So we used 100, if you remember, so you can use higher values. People sometimes go to 2042 or 2048, sorry. So people go even that high, 2048 or 100, 1024. So it depends on how big you want to go and whether you can get a better representation of the system. And sometimes even you are limited by the data that you have. Like in this case, you had only 1 molecule in 6. So maybe the machine did not get trained pretty well in identifying molecules with 6 wings in the system. So you can be also limited by the data that you have there. So you can try one is to change the number of bits and bits that we used in the generation and see whether it changes something. Or also use the regressor model, random forest regressor. The difference between regression and classification is you're trying to predict something which is categorical or continuous data. So in this, we had some categories, right? 0 number of wings, 1 number of wings, 2 wings, 3 wings, 4 wings. This was like categorical data. So in that case, we used classifier. And if you want to use a regressor, it means that you're going to predict something that is continuous. And that can be something like molecular mass. So molecular mass, you can actually bin it, but it's something which is continuous. And for that, we would need to use a regressor. So the code change will be here. So instead of classifier, you'll be using random forest regressor. And you can have your Y values to be molecular mass instead of number of wings that we predicted here, right? So right here we have number of wings. So instead of number of wings, you can try to get molecular mass and try to see whether that representation predicts the molecular mass, right? And we'll be using the random forest regressor model in the PyMed Gen thing. So you can try it out there too, but you can just give it a try here. And if you have any questions, do let me know. So do you have any questions on RDKit thing? Okay. So if you have, you can keep trying on this, and if you have any questions, you can type it into the chat or let me know. We'll take like 5-minute break now, and when we get back, we'll be doing something similar for periodic systems. This was just single molecule. We'll try to look into periodic systems, and we'll look into inorganic systems to be specific, and not organic periodic systems. We can even look at organic periodic systems like organic crystals, but we'll do the inorganic things. And we'll try to do something like this and predict the formation energy for that crystal and do a machine learning model to do that. Okay. So we'll take a 5-minute break, just walk around, maybe do some exercise, and we'll be back in 5 minutes from now. Let's wait for one more minute and we'll get started. So here is the link. So we'll do the same thing with this book again. File, save a copy in Drive. So again, everyone see my screen with the notebook open?
Yep.
Okay, cool. Thanks. So at the top, I have a link for the survey. So it'd be helpful if you give me suggestions or comments. Tell me about what could be improved about this workshop so you can complete it towards the end of this workshop, which will be done in probably half an hour. So let me know what you think about it, and we can improve it in the further additions of it. Okay. So make sure you have a copy of it, and if there's copy of this, PyMedGen is installed with pip and not with conda. You can even install with conda, but there's an option to install it with pip. So if there's an installation with pip, you can directly install it in this Collab with pip install. So we'll be using PyMedGen, which is for periodic systems that we are going to see. And MatMiner is a library for generating features. And let's see how we could use those in machine learning. So click, it'll take some time for it to load. And you'll see that we start the runtime thing, and you would need to restart it. Yeah, sure. Let me share the link again. There you go. So anyone who missed the link, so this is the link. Some of the machine learning libraries are already in there. But you need to install some chemistry libraries if you want to work with. So let's see if it is installed. Let's try running a sub. Hopefully this works. Yeah. So if it works for everyone, please let me know, because there was some error in the versions earlier, and I thought I fixed the versions. Okay. So yeah, this is very specific that you would need this 20 version, or else it won't. So yeah, if someone who's new to installing packages, so pip install is a way of installing it, and this thing that I put in is the version that you want. So you can specify the version that you want, or it will get the latest version. Yeah. So this is a 2020 version that we are trying to use so that this thing works. Okay. So the core package in PyMedGen is again the structure package. So core has structure. You can use molecules too in this. So there's a molecule class and a periodic structure class. But it does not provide the functionality that RDKit provides for molecules. So it's okay, but not too great for doing chem informatics stuff. But it's very good for doing periodic structures. So if you have a periodic structure, you can try to manipulate it, change things, and that's what we are going to do here. And then a little bit of machine learning with that thing that we have. So we can also generate slabs. I don't think we'd have so much of time to do that. So we can generate input structures for running quantum mechanical calculations, like things in Quantum Espresso or WASP or any other package that you can think of. So to start with, we'll get the CIF file. CIF is Crystal Information Format. And that is a way of, that's something similar to PDB, and but used for materials usually. And that's what we are going to get. We are going to get the NaCl for that. And once we generate a structure, we can generate it from the file. Just like we had smiles mole, the chem.mol from smiles, or chem.mol from file, or mol to file or something like that. So we would generate it from files. You can even generate it here if you pass in some parameters, but the parameters that are required are lattice parameters. So we just take it from the CIF. So a unit cell, in this is the unit cell of NaCl, and you can see the ABC, the vectors along ABC, and this is a cubic cell because all of them are equal, 90 degrees, it has volume, and it has the lattice parameters too, the A vector, B vector, C vector. And where is it? Okay. So that is the way it is written is you have a crystal structure, right? So you have in a crystal structure atomic sites. So it goes from sites. This is one site, and each site has a species, and then each species has coordinates. So these are the coordinates for those. Just like molecules, we went from molecules to atoms to bonds. So in this, we'll be going from a unit cell to a site which has XYZ coordinate, and from a site we can go into the element, just like we did in RDKit. So there are other options, pretty cool options that we can do in this. This is the NaCl structure. So if I want to replace NaCl with KCl, right? So I can just say element Na. So element is a object that we create. So as I told you, each of those sites is an element later on. So you go from periodic sites to finally an element. So we are saying replace this element with K, with potassium, and then we get a structure for KCl now, right? So this is what it looks like now, KCl and all these points and what it is. Right? So this is how replacement of things is done. You can play around with the options that are present. And sometimes you would need to generate a supercell. Let me just go back and use this NaCl itself instead of KCl. So if you want to generate a bigger cell for simulation or doing some analysis, what you can do is NaCl is what we need, and just multiply it with the vector to multiply in each dimension. So if I want what dimension was it? So 2 × 1 × 3 supercell, that means 2 along the x-axis, 1 along the y-axis, and 3 along the z-axis. So we are repeating the cell in each of those directions. So we'll say this, and it'll give us a bigger cell now. So if you see these lattice vectors, these are multiplied. This was a cubic, if you remember. All of those were similar. All of them were same. But now this is twice and this is twice because we multiplied it. And we see the number of sites have also increased. So this is how we would generate a supercell in PyMedicine. And yeah, I think these are some basics that we would cover in periodic cells. And this is some exercise for you to work with, is to generate a BCC cell for this. lattice with coordinates 0.5. Maybe I should have told you how to generate it. So if you have structure, so this is the way of generating structure. So a structure requires a lattice, right? So it requires a lattice, it requires species. A species are these species, CS and CL, and it requires coordinates where those coordinates are. So in this, if you want a body centered cubic lattice, you would say CS in between the center is 0.5, 0.5, 0.5, and the other is CL, CL is 0. So that's what we need. So here we would need lattice dot cubic. You can generate a cubic lattice of what is it? Any value, let's just say 5, and then we need to pass in the elements. We need this, and we need the relative coordinates for them. So 0.5, 0.5, 0.5, and then the second would be 0, 0, 0. Hopefully it works. So this is your cesium chloride structure. So it's a cubic, and you can put in a lattice constant. I'm not sure what is the lattice constant here, but you do something like this and you get CSE. Okay, so try replacing any of the 2 chlorines with bromine, or all of the chlorines with bromine if you want. And then if you are interested in looking at what things are present for it, what methods are present, so you can just look it up. So it has a large number of methods. So you can add oxidation state, guess oxidation, and you can get Cartesian coordinates, atomic numbers if you want. You can even get the composition of something. And this is what we'll be using for machine learning later on. You can get the distance matrix. Okay, so supercell is okay. So a supercell is a bigger cell. What we are doing is a unit cell. In crystallography, we have a small unit cell. Okay, and this is a periodic system. So the unit cell repeats again and again infinitely to generate your crystal. So if you want to generate a larger cell, so sometimes you want to do stuff on larger cells. So some calculations and other things, you can't just do it on a small cell. So you need to repeat it so that you get enough of atoms to do some analysis on them. Like if you want to generate a big surface and put a molecule on top of it, you'd need a larger surface. You can't use a very small thing and put something on it, but because it repeats periodically. So this supercell is just multiplying the unit cell along XYZ directions. So if you have in this case, what we are doing is we have NaCl unit cell, which is a small cell. And then we are saying extend it 2 times along the X, once along Y, it will be once, and 3 times along Z axis. So that's where we generate a larger cell. And you can see the number of atoms have increased. It's just periodic thing that we did. We try to extend it. And if we use this structure, we can later on do some analysis on this. And some of the quantum mechanical calculations need a bigger cell. Like if you want to adsorb some species onto it, you want one species, one molecule on top of some particular area. You need to create a bigger cell. So that's where generating supercell comes in. It's a periodic thing that we do. Okay. So there are other things as DataFrame. You can get distances. There's a way to replace species. We'll look into. There's replace and replace species. So we did replace species, which was replacing all the species with K. So if you do replace species, you do that. But if you do replace, you can replace one of the atoms with the other atom. So what we did here right now is CSCL. So we have this species, and if you want to replace it, say dot replace. Let's replace the second one with BR. So that means this is 0 index. This is 1 index with BR. And, so that is what we did. So we had CSCL, but we replaced only one of them by BR. Okay. So any questions until this point for periodic systems, generating periodic systems, or replacing something, replacing one atom by the other atom? Okay. So let's go into how these things are arranged. So as I told you, there's a structure that we looked at first, and a structure goes into sites, is made of sites, and you can see periodic site. So this is a site, and each site is again made of elements. So if you do periodic sites, you'll get all these sites, right? A list of sites. So then you can choose a particular site and look at what element it is now. So it's element Na. So this is how we are going to get go from structure to site to elements. So yeah. You can try yourself to explore some of the methods that are available for sites and elements. And if you do DIR of them, you'll probably get something. Try to explore some of this. You can get ionic radius of that and ground state term symbol and all of them. So try exploring some of this, and we'll do this for a couple of minutes so that you have time to explore it for sites as well as elements. So this is for elements, and you can do the same thing for sites. Try to explore some of them and see what it gives you. So do you have any questions at this point? There are ways in which you can generate slabs for simulation once you have the structure. And I think I do have a slab generator imported. So it's called slab generator. And you can pass in the structure and generate slabs if you want. If someone is familiar with that term, you'll recognize that. So you can if you give Miller indices, it can generate those slabs that you want and then do automation for that. I think I'll cover some of them in the next one, if possible, how to generate slabs and submit calculations. And also adsorb species on the surface. Okay. Any questions, or shall we move on? So if yeah, so we'll do the same thing that we did for RDKit, right? So we generated the representation. That's what everything is about, generating representation. So people have generated many models, and you can use some of those to do this machine learning. But where things are very critical is the representation. So how well you have represented the data that you want. And if your representation is not good, your prediction won't be good. So everything boils down to that now. So in this case, what we are trying to do is predict the experimental formation enthalpy. And this load data set is from Mat Miner that we used. And if you look into the documentation of this, there are many data sets that are available right away. And that could be directly used. So I'll be just loading one of the data set. And you can see there are 1, 2, 7, 6 entries here. And there are some data here, right? So what we'll be doing is we'll be using the formula and experimental formation enthalpy, energies from experimental results, and try to predict these given the molecular formula. Okay, that's what we are trying to do. Any questions until this point? So let me get the prediction thing clear first. And these are continuous values, as you can see. These are not classes. So we'll try to use regression and not classification. So the idea is to get the formula and experimental data. And as you can see, some of those experimental data have NaN. So these values are not available. For machine learning model, we don't want NaNs there. So what we'll do is we'll drop all these NaNs when we generate it. So the way to do that in pandas is drop NA. So it'll drop all the NaNs and give you data which has no NaNs. So we end up with 1196, which have all experimental values. We have a molecular formula for them. And we are almost ready to train another machine learning model right now. So again, it's the same problem, right? So we have molecular formula as a text, but we would need to convert it somehow into numbers so that we could use it for the input. We have the target values, but we need to convert this representation. We have a better representation. So that is where the Mat Miner comes in, and it generates material properties or features that we want from these things. So first of all, this is a text. Let's convert into something more useful, and it is called a composition object. So there's a way to do it is string to composition. And composition, if you remember, is one of the things that you can see even here. So if you would do NaCl dot composition, it would give there are 4 NAs and 4 Cls. That's what the crystal structure was, right? So it converts, it creates an object called composition, and there are many other things that this can do with, if you look at the IR of composition. So it can alphabetical formula, average electron, elements, fractional composition. There are many things like oxidation state, gas, and many things that you could do with this. So first of all, we'll try to convert the string that we have into this object. This is very similar to what we did in RDKit, was to convert smiles into the molecule objects. So here we'll try to convert string to composition, and we'll call that thing as composition, and the input is the formula. Right. And once we do that, we see we have created a composition object now for each one of those. This is very similar to RDKit thing that we did. Right. So once we have composition, we need to generate representations, and this is where we are using Mat Miner. So all of these features are from Mat Miner. So it uses stoichiometry, it uses elemental properties, it also gives valence orbitals and ion properties. Right? So these are some of the descriptors that we are going to use, or features that we are going to generate, and we are going to generate multiple of those. And we'll see how many features we have and what features we have once this is generated. Right? So this is creating the object for features, and then we'll try to featureize it. So once it is created, we can see how many features we are generating. So we are generating 145 of those features. And what are those 145 features? We don't know yet. We can see them once we generate them. So feature calculator is this thing, and feature-wise data frame. And the input is composition for this. Input column is this composition. So we say column ID is composition, and then we get the descriptors, the features back. Now it is generated, you see. So we had these 3 columns, and these are the 145 features that we have now. So there's something called norm that it has created, and some other things, maximum number range. You can go into the documentation and see what each one of those mean, but some things would be more readily understandable. Something like there is an atomic weight for this, the maximum atomic weight reported somehow. There's melting temperature, minimum melting temperature, maximum melting temperature, and other things. So you see, there are a lot of features that we are generated. So now these would be the things that we would use for training, and all of these features, just like zeros, ones that we used, we are going to use these values as the input, and we are trying to predict the formation energy for this, which is this column. Okay. Any questions until this point? Because next thing we are going to do is train a model. Okay. So if there are no questions, again, we set the X values and Y values. So X values are feature labels. So if you remember, feature labels are all list of all of these. So get everything from here. So the values and this, maybe I should have printed. Let me show X is X of 0, and Y is Y of 0. So this is X. So it's a long 145 dimension vector that we have. Right? And you see there's a false value somewhere here. So that will be converted into zeros and ones later on. So we don't need to worry much about that. And this is the Y value that we have. So again, we are splitting it into 80 for training and 20 for a test. And the thing is already generated. Over here, we are going to use regression model because this is a continuous data, as you saw, and not discrete. So model.fit again and model.predict for predicting that. The metrics that we are going to use here are different. We're not going to use the confusion matrix. Rather, we are going to use R square or mean absolute error or mean squared error for the evaluation. And we did something similar here in this code to get the predicted values, and we put in predicted and the test values to see how good a relation it is. Right? Look at R square values, it's 0.82. Not very good, but it's decent because what we have done is we have just put in a random forest regression model with some data that we generated. So there can be more things. You can refine the features that we have and see which are the ones that are really important and put those in. So or add more features. But given this very simple model, it's pretty impressive that you can get up to R square of 0.82. So if you want to visualize it, it'll be just a scatter plot that you're going to do, and you're going to plot X and Y. And these are just to get a straight line to fit. So X, Y, X equal to Y. And if you see that plot, you see that these are the true values, these are the predicted values, and it's pretty decent, not too bad either for a very simple model that we have here. So yeah, so to do it yourself, you can try to explore other models that are present in MatMiner and train some models yourself to get a better result than this that we have. And you can even go to scikit-learn. Let me show you what it is. Okay. So scikit-learn, sklearn has various models. We used random forest. There are a lot many other models that you can use, and try to see which model gives you better better prediction. So should you either try some of those models too. And if you have any questions, please let me know. I think this is a very, very short introduction on PyMedGen, because some of this will be discussed in the next one when we automate things. So I did not discuss a lot of slab generation, adding molecules onto the surface, but look into the machine learning aspects of it, where we generate things from it and generate features. We have values and do it. So there are other data sets you can try to look for and have this model built, predict some things for you. So I think this is the end of what I have for you guys. If you have any questions, you can stay here and ask me those if you have any problems doing it. This is a link for the survey, so please I can just paste it in for you guys if you want, but it's on top of the thing. So please let me know what you think about this workshop. So the next time it is offered, we can make some changes so that it will be more helpful for you guys. And if you have any questions, do stick around. Do follow the Facebook page for getting updates on the next workshops that we have. If you have any questions, please go ahead. You can unmute yourself. Let me stop the recording so that stop the recording.